Hello everybody, welcome back to the Gregorius Maths video. Today, if you saw the last video, I talked about the Coriolis effect and how it differs in the northern and southern hemisphere. And I said that in a later video I would tell you where the formula for the Coriolis acceleration actually comes from. And today is when I do that. And I'll also talk about what the other fictitious forces are, so to speak. So, why do I title the video Newton's second law is false? Or I don't know what I've titled it at the time of recording, but something along those lines. Well, again, it's kind of clickbait. It's pretty much clickbait, but the point I'm trying to make is Newton's second law holds in an inertial frame, which is a frame in which a particle that's not being acted on by any forces has a constant velocity, basically. But in a non-inertial frame, Newton's second law doesn't necessarily hold. And an important example of a non-inertial frame is a rotating frame, right? Such as, the Earth is rotating. That's an important example. So if we consider an inertial frame S with bases, let's say S has bases E1, E2, E3 as its basis, and let's say we have S prime, which is rotating, and from the point of view of the inertial basis, it has a basis of E1 prime, E2 prime, and E3 prime, okay? Now, since we're rotating with some angular velocity omega, from the point of view of S, these bases should satisfy that E1 prime dotted, or EI, I guess more generally, prime dot, i.e. the derivative with respect to time, should just be given by the angular velocity cross EI prime, okay? So, let us see how motion works in our rotating frame then, using this formula here and just plowing ahead with the differentiation. And just as a bit of notation, firstly we'll let our position vector x just be given by xi ei, or in the other basis xi prime ei prime. And we're going to denote dx dt with respect to s just to mean xi dot ei. And similarly, we'll denote dx dt with respect to s prime to just mean you differentiate just xi prime with respect to t. Okay, so this is just some notation. And now let's get into it. So, if the first thing, we want to examine like the motion. So eventually we want to figure out the acceleration. So first things first, let's figure out some formulas that we can link the velocity in S to the velocity in, when we look at it from the point of view of S prime instead. So, okay, let's do that. So if we write x dot, that's equal to, firstly it's just equal to xi dot ei, but if you differentiate this guy, it's also equal to xi prime dot ei prime plus, and now we use the product rule because this thing is changing over time, we can also differentiate this. So we also get plus xi prime ei prime dot, well, differentiator, whatever you want to call it. Now this should, from our perspective, satisfy this. So let's plug that in. We get this is xi prime ei x I dot prime. Saying dot prime sounds bad, so hopefully I'm just going to assume you can read what I'm writing. And then we replace this with just omega cross E I prime, like so. And since this is just a constant, we'll move it inside, and so we get xi prime dot ei prime plus omega cross, and then we get xi prime ei prime, but that's just x. And so therefore, we get that dx dt with respect to our first inertial frame S, the velocity from the perspective of our inertial frame S is just given by, well, dx dt s prime, this thing, plus some factor of omega cross x. So we have the velocity of our guy, how fast our Cartesian coordinate part is changing, but we also have to add in this angular velocity component, which accounts for how we're rotating. Okay, nice, fine, that's good. Now let's find the acceleration. So if we now compute x double dot, what do we get? Well, first things first, we just get that this is the derivative with respect to t of this guy. So we'll write that out as xi prime dot ei prime plus, and then just omega cross x, like so. And this is equal to, well, we can use the product rule on both of these guys. So this is equal to xi double dot prime ei prime plus xi prime dot ei prime dot plus omega dot cross x plus x dot cross, plus omega cross x dot, like so. This is just precisely the definition of doing this twice. So this is just d squared x dt squared with respect to s prime plus, and again, let's expand this guy as this. So we get xi prime dot times by omega cross ei prime, yep, plus omega dot cross x, and then plus omega cross x prime, like so. This is just equal to, so we keep this thing the same, so second derivative of x with respect to t in our frame S prime, plus, and now we get omega cross, because we just bring the xi prime dot inside, and then we just get that this is precisely just dx dt in S prime, plus, and then this just, there's nothing we can really do about that, so we just keep that the same. And then we're going to use our expression for x dot, which we got somewhere around here, like this one here, to say that this is just omega cross, and then we have, this is just dx dt in S prime, and then this is just omega cross x. So we have dx dt with respect to S prime cross omega cross x, right? Yeah. Okay, like so. Now this thing right here is the same thing. In fact, I'm not even going to bother writing all this out anymore. This is just da 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 plus this thing plus, and then so we got da 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 plus, we got now have two lots of omega cross dx dt S prime, and then we have this thing, and we have omega cross x, like so. Okay, so I'll just let you just do that in your head because I don't want to write that out again. Now, okay, what's the punchline? Well, In the inertial frame, what we have is that some force, if we have some force, is just given by m times by the second derivative of x with respect to t in s. But now, what does the motion actually look like in the rotating frame? Well, this thing right here, if we want to write m times by the acceleration in s prime, so ma but in s prime, well then we have to subtract all of these things, which are called the fictitious forces. And so we instead get that m times by d squared x dt squared in s prime is not just f, it's rather f minus, and then m times all of this. So we have m omega dot cross x minus 2m omega cross dx dt in s prime, and then minus m omega cross x, like this, right? And so when I say in the title, this clickbait title, Newton's second law is false, that is clickbait. What I really mean is that if we look at a non-inertial frame, then weird stuff happens, right? And the important example in this case is a rotating frame in which ma, from the perspective of the rotating frame, is F minus, and then this thing here is called the Euler force. This thing here is the Coriolis force, which we looked at last time, and then this here is the centrifugal force. And so yeah, I just wanted to make this note about the equations of motion in a rotating frame. And yeah, hopefully I'll see you guys tomorrow, and yeah, have a good day.